Word. So thank you everybody for coming. Today we have a very special talk by Max Bee-Lindgren. He's a student at Decatur High School, and he's attending the Research Science Institute run by the Center for Excellence in Education. He has been working with me remotely for about a month and doing some incredible research work on quantum computing, in particular, how to calculate the transitions, for example, from an excited state to a ground state in a quantum system. So what's called a transition matrix element on a quantum computer. So Max will give a presentation. It'll probably last about 20 minutes or so, and feel free to ask questions. So without further ado, Max, go ahead and take it away.
Thank you for your introduction. Yeah, I'm Max Bee-Lindgren. I'll be presenting on the two-state Rodeo algorithm, and more specifically, calculating those transition matrix elements. So what is quantum computing? The fundamental idea, I guess, behind quantum computing is the qubit, or quantum bit. So where a classical bit can only be in state 0 or state 1, the quantum bit can be in any linear combination of state 0 and state 1. Although this linear combination, the absolute value squared, must be equal to 1. And the reason this is the case is because the magnitude squared of each of the components is the probability that when measured, the qubit is in 0 or 1. So because the qubit is like a physical system, it has to be in a state. So because of this linear or this ability to be in a linear combination, the qubit can theoretically hold much more information than a classical bit, although there are challenges associated with it. So how can we actually use these qubits? So there are many applications, some of which you've probably heard of, such as Shor's algorithm for decrypting and factoring big numbers, but that's not what I'll be focusing on today. I'll be focusing on the more physics-related applications, I guess. So one of these is identifying energy states of a quantum system. So up here, this is the spectrum for the electron, or the electron falling to the ground state of hydrogen from an excited state. So for simple systems like the hydrogen atom, we can calculate these values exactly, and they also are relatively easy to measure. However, for more complicated systems, such as atomic nuclei with many protons and many neutrons, or potentially multi-body systems, these energy values get much harder to calculate, and we can use quantum computers to calculate these systems. So there are a number of algorithms that do this, one of which is the Rodeo algorithm, which some of you may have heard of, and I'll be explaining in more detail later. What I'll be focusing on is a new application of quantum computing, which is calculating these gamma decay transition matrix elements. So for a unstable nucleus in a more excited state, it will fall to a lower energy level, and the matrix, or the matrices that guide this, are of interest to nuclear physicists. So how do we actually use these qubits and figure out and calculate these energy levels or transition matrix elements? So the basic idea is these quantum gates. They're similar to a classical logic gate, except they're represented as 2x2 matrices for a single gate, and then each additional qubit doubles the dimensions of the matrix. So yeah, I'll be focusing primarily on single qubit matrices, and there's some more advanced ones later on, but for now, single qubits are relatively normal. So the Hadamard gate is kind of the basis of a lot of quantum systems. What it does is it essentially splits the 0 and 1 factors, or evenly between 0 and 1. And so if you had a qubit in the 1 state, it would split it into half 0 and half 1. This phase rotation is similar, or it basically is semi-analogous to a time evolution, except it only evolves the 1 state of the qubit. So this is, well, I'll get into more detail on this phase rotation. And then for measurement, we typically project the qubit into the one state and then take the probability of success, which is just the state, so the qubit, and then times its complex conjugate. So this is a relatively simple quantum circuit. We start with a qubit in the one state, which is on the right here, and we apply the Hadamard gate, and then the phase rotation, and then another Hadamard gate, and then we measure it. So this has the effect of giving us this, or giving us this end state. And then when we take the probability of success and multiply by the conjugate transpose, we get this nice cosine squared function. So essentially the probability of success depends on this energy difference and this time over 2. And it's just a cosine function of that. So now we get into the Rodeo algorithm. So this is what ends up happening when we take multiple of these measurements. So with 3 measurements, there's still spikes at non-zero element or non-zero energy differences. And however, once we get up to 6 and 9 measurements, we only spike when the energy difference is 0. So this allows us to design a Rodeo algorithm, or a algorithm that isolates a specific energy state. So here we have a bunch of these circuits, or the lines of the circuit that we saw earlier, and now we couple them to this quantum system at the bottom. So the coupling is somewhat complicated, but essentially what we just do is instead of like ones in the gates, we use these identity matrices, and we use the object Hamiltonian instead of the energy of the object. So what this comes down to is this is one line of the quantum circuit for the Rodeo algorithm. So we still start out with something similar to the one state, except now we have the system instead of the one. And then we have the coupled Hadamard gate. We have this time evolution, and then you can see this will time evolve the system here. And then we have another Hadamard gate, and then just the projection operator. So what does this actually do? So this is the result of the Rodeo algorithm on with a number of different cycles on our example system. So you can see at 3 cycles, there are still obvious peaks at where the energy eigenstates are, and the size of the peak is proportional to the prevalence of that energy state. However, there's still a pretty constant noise to the system, and the peaks are kind of muddled together. So for example, this ground state is still technically visible, but it's pretty indistinguishable from this more dominant first excited state. Once we start to get up to 6 cycles, the noise is a lot lower and the peaks are a lot more visible. And then at 9 cycles, there's practically no noise, and the peaks for each energy eigenstate are fairly distinct. So just a word on the model. So we're using the spin 1/2 Heisenberg model, which is just a bunch of spin 1/2 particles in a ring. In our case, we used 10 of them, and we started them off in this nice alternating state. So we have spin down and then spin up and so on. So this is a nice state, or a nice starting state, because it's pretty symmetric. So we get a relatively small selection of non-zero energy eigenvalues. So the way the Rodeo algorithm works is we randomize the time for the time evolution. So what this does is it suppresses all the energy all the energy differences that aren't 0, because the gaps between the spikes and the cosines, because that distance is random, they'll basically all cancel out once we have enough cosines. However, we can control the amount of time the system evolves for. So that's what we do with the 2-state Rodeo algorithm. So we find our 2 energies using the original Rodeo algorithm, and then we set t to this quantity here, which is proportional to the inverse of the energy difference. So what we get is the probability of success, is now this modified cosine function, which will have a peak at, which will essentially peak at whatever we set the energy difference to. So this is the theoretical result. Here we set the energy difference to 5. Here's a peak at 5, and every other value is suppressed. So this is all well and good, but what can we actually do with this? So what one area of interest is those transition matrix elements. So what we do after we run the Rodeo algorithm on a system is we time evolve that system again. So the ideal result is we just have two states isolated. So in this case, we have Ci and Cj. These could be any energy states in the system. So we time evolve these states. So now they have this complex phase factor on them. And then we take the expectation value of some observable. And that gets us, that should give us this resulting cosine function that's proportional to the energy difference, or the cosine, the frequency is proportional to the energy difference, and the cosine itself is scaled by the two spectral weights of the energy states and this matrix element that we want here. And then these diagonal matrix elements are equivalent to the absolute value of, or proportional to the absolute value of the spectral weights squared and the diagonal matrix elements. So this is the full process. To actually get the energies and the states we want, we first run the Rodeo algorithm on the system and pick out our states. Then we run the two-state Rodeo algorithm to isolate only the states we want and filter out all the rest. And then we time evolve that resulting theoretically two-state system and calculate the expectation value for the observable at a given time. And then we repeat 3 for a bunch of different time evolutions. And then we take that resulting data and fit a cosine function. So what does that data come out to look like? So with this is for the ground state and the first excited state, and the exact matrix element is roughly minus 0.56, 0.57. So with only 3 cycles on the left here, there you can see there's an additional cosine that's causing some oscillations. In fact, there are 2 cosines here that are causing oscillations. So this is the effect of an additional energy state that's crept into our theoretically 2-state system. However, we can compensate for that with a 3 cosine fit, which is not that much more complicated than the single cosine fit I showed earlier. And we can get a pretty good estimate for the matrix element. However, if for whatever reason that multi-cosine fit is not possible, we can still get a reasonable estimate with a single cosine. And then at 9 cycles, all the additional energy states are entirely filtered out, and we have this really exact estimate for the matrix element. So what about some less dominant states? So here we have states 4 and 5, which are the 3rd and 4th excited states of the system. So here you can see with only 3 cycles, there are a lot more cosines, and so a lot more unwanted energy states in the system, causing a significant amount of noise in the data. So we can compensate for some of this with a 3 cosine fit, although it's a lot worse than the 3 cosine fit when there are only 2 energy states, or when there are only 3 energy states. And then even though the state is pretty noisy, the single cosine fit does a reasonable job of estimating the matrix element. And then with 9 cycles, the data is a lot cleaner, and we can cleanly fit it with the 3 cosine fit and still get a really precise matrix element estimate. So I will say some notes and caveats to these results. We simulated these on a classical computer, so there were no gate errors, and we were able to have perfect knowledge of the system. So in reality, these estimates would have more error, as we don't exactly know the spectral weights of the energy eigenstates. So there'd be error from that in addition to the error from the fit. And also the 9 cycles, so the really clean result on the right is unfeasible given the current quantum computing technology. So we'd be stuck with the 3-cycle Rodeo algorithm, which, as I showed before, can still give a reasonable fit. It's just less precise than what would be optimal. So for future research, I would like to apply this 2-state Rodeo algorithm beyond nuclear and atomic physics. So while the matrix element calculation part is relatively unique to nuclear and atomic physics, the 2-state Rodeo algorithm itself could potentially be applied beyond that field, although I don't really know what those applications would be at this current time. I'd also like to test its performance with systems that have a tight cluster and or notable degenerate eigenstates, and see how the algorithm functions there. I'd also like to test it with a more complicated observable. So the observable I used was the sigma z with just the Pauli Z spin matrix. And I'd like to test it with potentially a complex observable or a random observable. And then I would also like to implement it on an actual quantum computer to test its functionality and see how much or how accurate of an estimate we can get with a real quantum computer. And finally, I'd like to thank my wonderful mentor, Dr. Dean Lee, for giving me inspiration and helping me through this project. I'd also like to thank my tutor, Dr. John Ricker, for helping with my presentation and advice on scientific writing in general. I'd like to thank my physics professors, Dr. Rollison, Dr. Meyer, and Professor Howard, for teaching me basically everything I know about physics. And I'd also like to thank my first week teaching assistants, Lucy Kai and Ishan Kare, for helping me with LaTeX. And finally, I'd like to thank the Research Science Institute for giving me this wonderful opportunity, and the Center for Excellence in Education and the Massachusetts Institute of Technology for putting on such an amazing program. Thank you, and I'm open to questions.
Thank you so much, Max. Boy, if I could give a talk like that when I was in high school, wow, that would be incredible. So I'm sure there are some questions, so feel free to just unmute yourself and ask a question.
Dr. Sandoval?
Jenny. Yeah.
Among the amazing results you've got so far, was there one that was the most unexpected for you?
I guess I'll say this multi-cosine fit took a lot of tinkering to get right, and I was not expecting it to perform so well. And I was also not expecting it to work with this 3-cycle system that well on the left, because what's happening with this 3-cycle system is there, in addition to the 2 selected eigenstates, there are also a number of additional eigenstates that have crept in with relatively equal probabilities that results in potentially like a 6 or a 10 cosine theoretical fit. However, the 3 cosine fit was able to give a reasonable approximation. That was somewhat surprising.
Thank you very much. Good luck with the next.
Thank you.
I'm sure that there is an obvious reason for this, but why are the cycles in multiples of 3?
It doesn't matter. That's just what we chose. You could do like 4 cycles or potentially even 2 cycles, although 2 cycles is still sketchy.
I don't know. Could you go back to slide 10 for me? So I kind of got lost in how this related to what you were doing.
Yeah, so this is just our system that we used. So the Hamiltonians defined on the right. So we simulated, or we calculated this Hamiltonian, and then basically took the non-zero eigenstates and simulated the algorithm from there.
And is this in any way supposed to be a model for a nucleus? Like how
No, it's just a good example system.
Okay.
I will say there's nothing stopping you from using a better model for a nucleus besides like computation time.
Very good. Are there other questions? Okay, if not, let's thank Max once again for a very, very nice talk. And thank you to everybody for coming. Feel free to hang around and talk afterwards if you'd like to. So thank you for coming, everybody.
Thank you.